Okay. Sorry. Okay. Yes. So this is specifically true about Q. You can have a similar formula that's true about number fields, so finite extensions of Q. It's not going to be true about R because R is the completion at infinity, and so R is a local field. It only has one prime. It's not a global field like Q, which has many primes. So a formula like this is how the different primes in a field interact with each other, and R doesn't have other primes than infinity. So it doesn't, any QP doesn't have a formula like that either. The local fields only have the one prime, so you can't do that. All right, so now we're ready for today. So today in local fields, we're going to basically do what we did yesterday, but now with symbols, and I'm going to tell you the real words that go with the things. So we're going to start with K any field. Let K be a field. But we assume that K has a discrete valuation which is a group, sorry, I'm going to write it, group homomorphism V from K cross to Z. Okay, I want to point out that the group operation on K cross, so these are the units in K, so K, since K is a field, it's everything except 0, right? So this is the symbol that I use for essentially K, and you take away 0. The operation on this group is multiplication, and Z is only a group under addition, right? So the operation on this group is addition. So it's a map, right, that sends multiplication to addition, just like we talked about. Right, like the group homomorphism immediately implies that property of evaluation that is surjective and such that, and then we just give the ultrametric inequality, right? This thing that will give you the triangle inequality once you apply it to the absolute value. I want to call it still the triangle inequality. There's no triangle here, but okay. So we'll want the valuation to be surjective. So we want numbers in K that have like every value, the positives and negatives. I mean, if it's not surjective, the image is going to be isomorphic to Z. So you could just say, you could just rescale, right? So say there was something of valuation 2, but nothing of valuation 1. You could just like have all the valuations, and then you would have it go in Z. So I mean, the surjectivity is not that big a deal. It's just to say like there's something that has valuation 1, right? Like it's not like valuation 3 and then you have to bring it back down to 1. Okay, so you want it to be surjective and such that this is satisfied, and we set the valuation of 0 is infinite, right? So that's the last part. So that's a discrete valuation, like that's the definition. And what I introduced last time, right, you know, so V sub P from last time is a discrete valuation on Q, also on QP, the p-adic numbers, right? So that was our example. That's how we started yesterday. So now we'll put ourselves in the general situation where we just have a field with a V. And then just from this data, right, this data of a field and evaluation, then we can define a set A inside of K, which is all X and K, such that the valuation of x is greater or equal to 0, right? The good numbers, the ones that we at least do not dislike. Okay, this is a ring. Called the valuation ring of Kv, right? I mean, you know, if most of the time we'll just say the valuation ring of K, but if K happened to have many valuations, then you would have to say which valuation this is the valuation ring of, right? But so this is called a valuation ring. Why is it a ring? If we go back to our properties, because it's a group homomorphism, if you have two numbers with non-negative valuation, when you multiply them together, you know, the valuation will only get bigger, so it will still be non-negative. And when you add them together, the valuation won't get smaller, so it'll still be non-negative. And certainly the identity of your field has valuation 0 because this is the valuation is a group homomorphism, right? So group hom has to send the identity to the identity. So there's definitely an element in this set. So it's a non-empty set that's closed under addition and multiplication, and actually subtraction. So it works as a ring. All right. And we can also define an ideal M, which is all x and a or k, you know, such that the valuation is strictly greater than 0. These ones are the actually good ones, right? Like not the ones we don't mind, the ones that are actually get positive points from us. And you can show that this is an ideal in A, because all it needs to do is like absorb multiplication. And if you have, right, an element that has positive valuation and an element that has non-negative valuation, then you have a positive plus a non-negative, so it's certainly positive again, right? Like the one that's like not quite an ideal can't mess you up enough to bring you out of the ring completely. And then, right, we discussed, I mean, we discussed in that setting last time, but the same arguments work. Like I mean, it's like so the same. This is in fact the unique maximal ideal of A. And to show that, it suffices to show that A minus M, right, set minus is all units. Right? So this means like there's literally nothing you could add to this and still have it be a strict ideal. If you add a unit to an ideal, you automatically get the whole thing. Okay. Well, I guess that's going to go on the other page. I'm not going to cram it in there. Okay. So that's, you know, mini little proof, right? So if x is an A minus M, then the valuation of x is 0, right? Because like everything in A has non-negative valuations and everything in M has positive valuations, so that's that, right? And recall, since x belongs to K, a field, x has an inverse, right? X, y is equal to 1. X is not 0 since the valuation of 0 is infinity, right? But I just said that the valuation of x was 0. So certainly x was not 0 to begin with. And so at least in the field, it has an inverse, right? That's not you know, that's not in debate, like x is a field. But the question is, can I make sure that y is actually in A so that x is invertible in A, right? So we must show that y belongs to A, then x is a unit in A. Okay, but now that we have this equation, right, but xy is equal to 1 implies that the valuation of 1, which is 0, is equal to the valuation of x plus the valuation of y, and the valuation of x is 0, so the valuation of y is 0, and y is an A. Okay, so if you just start with a field that has a discrete valuation, you can automatically define, a ring, which I will think of as the integers, right? Like the good numbers. That ring has a unique maximal ideal. And because this ideal is maximal, right, we can also write / define, I guess. Okay, so I tend to use like lowercase k. Sarah uses k bar, which I do not like. But anyway, that's just A mod M, the residue field. Okay, so this is what Christelle likes. This is Sarah's notation. Okay, I don't like it because to me that should be the algebraic closure of K. I mean, this isn't happening in this book, so I guess, I don't want to put thoughts in Sarah's head. I'm sure his thoughts are way better than mine. But maybe he was like, I'm not using that hat, so might as well. But that's just confusing to me. So anyway, I will probably use all three in an attempt to confuse all of us with the notation. All right, so now I want to say a little bit more. I was able to say all these things, but in fact, A is a PID, a principal ideal domain, and M is its unique prime ideal. Okay, so that's a bit more. I said that M was a unique maximal ideal, but actually there's no other prime ideals inside of it either. All the other ideals are not even prime. And, A is forced to be a principal ideal domain, which is pretty cool. Okay, so it's certainly a domain because it's inside a field, right? So there's not going to be any zero divisors. So we already put ourselves outside of that, horrible situation. So we just need to show that all the ideals are principal and that this ideal is prime. Right? So prove, let pi, it's going to end up being an A, be such that B of pi is 1, right? This is my surjectivity. Like I want an element that has valuation 1. So I take it, a priori it's in K, but A is everything that has non-negative valuation, so it's also in A. And then for X and K, if the valuation of X is, some number N, then we have, I'm going to go on the next page, right? But if I take any element in K and I take its valuation and I do U is X divided by pi to the N is a unit in A. Okay, this is because the valuation of x is the valuation of u times pi n. So that's the valuation of u plus the valuation of pi to the n, right? But this has valuation n by hypothesis, and this has valuation n by our homomorphic property, because pi has valuation 1. So if you have n of them, that has valuation n. So it forces the valuation of u to be 0. Right? And we just proved that everything that had valuation 0 was a unit in A. So in particular, the elements of A are of the form, actually it's right here, right? A unit times pi to the n, but the elements of K as well, right? The difference between the elements of, that are in K but not in A is what the n is here. The elements of K have negative n's and the elements of A have non-negative n's in there, but they're all a unit times the power of n. And a unit in A, right? I mean, it doesn't really mean anything to say a unit in K, it's just non-zero. Okay. So now, I'm not going to fully prove that every ideal is principal, but I can show that every finitely generated ideal is principal, which hopefully will be enough to convince you, because there's like so many more pages of notes that I want to get through. Anyway, so now suppose that I is an ideal in A. Okay, so this is my notation for is an ideal in A. So it's like normal group. I just feel it fits well. I don't think I'm the only person that does that. Then, right, x is u pi to the n, y is v pi to the m, right, for some uv units in A, and without loss of generality, maybe n is greater than or equal to m. They're both greater than or equal to 0, right? I'll just put the one with greater valuation first. Oh, sorry, I did not tell you what. That's my bad. I need to add some stuff. What are x and y? There we go. With I generated by x and y. Sorry. Okay. So my point is, right, I want to take any ideal in A and I want to show that it's a principal ideal. So I'm going to start with, something I can handle, which is an ideal with 2 generators. And I'm going to show that has only 1 generator. So that means that whenever I have finitely many generators, right, I could take I can bring it down until I have only 1 generator. And you'll see, I just want to get the flavor, like, why does this, like, this field just has this valuation and like all of a sudden the ring is a PID, like, what the heck, right? And it's because of the valuation. I mean, obviously it has to be because of the valuation. Otherwise, everything would be PIDs. Oh my God, what a world. Okay, so if I have a little element in I, right, then A is A1x plus A2y. That's what it means to be in the ideal generated by x and y, which is just like A1 u pi to the n plus A2 v pi to the m. And now I can factor out pi to the m. A1 u pi to the n minus m plus A2 v, right? Because I assumed that this one was greater than or equal to that one. So this is non-negative. So this is still an A. Oops. Right. So A belongs to pi to the the ideal generated by pi to the right? The lower one of the 2 exponents, right? Conversely, since y, which is v pi to the m, belongs to I, we have that pi to the m belongs to I, right? Because I can multiply by the inverse of v and stay in this ideal, so the ideal generated by pi to the m is inside I, and we have equality. So sorry. Sorry, I'm skipping steps. I've taught this a lot at the graduate level, and I have to, like, get back down to my algebra. Right, so if A is in this ideal generated by pi to the m for every A in I, this means that the ideal I is completely contained in the ideal generated by pi to the m. And then conversely, because I can put pi to the m actually inside of I, it means that this ideal is inside of I, and so they must be equal. Right, so I thought I needed two generators, but actually I really only needed like whatever pi to whatever power. Like that's all the ideals that there are. So all ideals in A are not only principal and generated by, some pi to the n for n. Well, no, strictly greater than 0. We're not going to say that the whole ring is ideal. Yep. That a Dvr is? Oh, sorry. So the question is, did we assume that a Dvr is Noetherian? And I haven't defined Dvr yet, but yes, when I define Dvr, it's going to have to be a PID. So it's automatically going to be Noetherian. So right now, I'm kind of going the other way from what you might be thinking. I started with a field and evaluation, and I'm proving that the valuation ring is a PID, therefore Noetherian, right? So I haven't like given a name to that phenomenon yet. And then when I'm done proving like all the things that A is, I'm going to say we call that a DVR. And so a DVR will have this property. Oh yeah, we don't know that. So I haven't like talked about that. Yeah. And like I can write more about it. I'm just trying to get to completion. So I don't, I just wanted to be like, here's a flavor. So yes, apologies on that front. Blah, 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 blah. Okay, so it's a PID. Okay. Okay, so now, yes, sorry. So now there's an obvious like top ideal, which is the one generated by pi, and then all the other ones, they're not prime, right? Like pi squared, the ideal generated by pi squared is not prime because pi times pi is in pi squared, but pi is not in the ideal generated by pi squared, right? So now that we know all the ideals of A, we see that only the ideal generated by pi is prime. All others are not. So, M, which was the ideal generated by pi, is the unique non-zero. I don't know if I forgot to say that. Non-zero prime ideal, right? 0 is always there, is always prime. Okay, is the unique non-zero prime ideal of A. Oh, so because, okay, so that's a good, pi is not unique, right? So I started out fixing an element that has valuation 1. And if I picked a different element that had valuation 1, it would differ from this pi by a unit in A. So it would not matter. They would both generate the same ideal. Like pi would be the same ideal as generated by pi prime, and everything would just go the same. So though pi is not unique, all of the ideals are unique because they can only differ by a unit in A. All right. Oops. So now you see my thing, right? I mean, like, I do one beginning and one end, and then like one white in the middle, and I just make more white pages. The reason for that is that when we started going remote, I would forget to start recording class, like, because it was a new thing to do. So on the first slide, I would put this class will be recorded, both like for legal reasons to like tell them they would be recorded, but also to like remind me to start the recording. And then I'm like okay at public speaking, but I'm actually a deeply awkward, introverted person in real life. So I didn't know how to end lecture. So I was just like, I'm going to put a slide telling them that it's over, and hopefully they'll just like click end to the meeting. So anyway, and now it's 2 years later, and like that's still what I do. Even when you're in person, it's a lot less awkward to end the class. I can just stand up and leave. I guess I could have just like ended the meeting on my end and not worried about them. Anyway. Okay. So yeah, so let's do that. Let's define it, right? So that was the end of that proof. Okay, so we saw that A is very special. Right? And so let's give that a name, right? So a PID, so principal, ideal, but also domain. It has to be a domain that has a unique non-zero prime ideal is called a discrete valuation ring, or DVR. Okay, so we see that if you start from a valued field, a discretely valued field, then the valuation ring inside of it will be a discrete valuation ring, according to this definition, which actually has no valuation in it, right? But the unique non-zero prime ideal is what tells you the valuation on that, right? So in a PID, every element can be factored into irreducibles. So if you have a unique non-zero prime ideal, this means that up to unit you have a unique irreducible element. So that gives you your pi, and then you can get going with that. Okay, and so pi is also special, right? We call any element pi with valuation of pi is equal to 1 a uniformizer. For A. There's more words. Like people call them different things. That's just a uniformizer, but I forget them. It's usually pretty clear what they mean. It's sometimes denoted also like lowercase t. If you see a pi, a lowercase t, or this letter, which like kind of looks like a W, but is actually like a cursive pi. Like this thing here. It's like var pi or what. Anyway, when you see that, you know the algebra is going to get serious. Okay? And so I just want to point out that a ring with a unique maximal ideal is a local ring, and not all local rings are DVRs. Right? So I started out like it was pretty easy to show that A would be a local ring, that it has a unique maximal ideal, but then there was extra work to be done to show that actually that maximal ideal, that it was a PID, that all ideals are principal, and that this ideal is actually prime. And in an example, of a local but not DVR is the ring, K is any field now. Of power series in x squared and x cubed. Let me just, so if I just did like the normal, so this is meant to be like double square brackets, right? Is the set of f the form a n x to the n, but n has to start at 0. Right? So it's the power series with no negative exponents. So but they can go, infinite that way. So you take the power series in x squared and x cubed, right? Which is actually like almost all of these, but none of them can have an x term, right? So you can have the constant, and then you can have the x squared, the x cubed, you can have the x to the fourth because that's x squared squared, and like everything else you can do, but not the x. So it's like a little weird, okay? So it's a local ring, but it's not a DVR because its maximal ideal is generated by x squared and x cubed. All right. Sorry. So I started with the field and got a DVR out of it, and we could do it the other way. We could start with a DVR, just have like I have a ring A, it's a DVR, right? It has its PID has a unique prime ideal, and then I could take K, its field of fractions, and that would be a valued field with a discrete valuation. So like the whole situation is like you can start from wherever you want. You can start from numbers that you like, and make them a valuation ring in a field, or you can start with a field and like identify a valued field and identify numbers you like in there, and it's the whole story either way you do it. So Sarah actually starts with the ring and then makes the field and the valuation, and I started with the field and the valuation and I made the ring. Okay, so that's half of what we covered yesterday. So now let's talk about completions. I'll go 10 more minutes and we'll deal with the rest when we can. Okay, so for today, probably until tomorrow, I'm not going to justify this anymore, right? It'll just be like, this weird mathematician in a weird corner studying weird rings. Like, I don't know, right? This just happens. But there will be, once I can, bring in the global picture tomorrow, there's a reason to do this. It's a weird mathematician reason, but there's a reason. I'm always like, no, but mom, you really want only one prime ideal. She would not think that that's a real reason to do anything. All right. So now completions. Okay, because like there's a reason why you want a DVR instead of not, and then there's actually you want a complete DVR. Like like if you want stuff, you want the nice stuff. So let's talk about completions. Okay, so same as before, right? And like as before, I mean like literally minutes ago, right? We have K, a field, it has a discrete valuation. A is the valuation ring, pi is a uniformizer, like all of that. And we can fix a real number between 0 and 1, then, right, absolute value of x, which is a to the valuation of x, is an absolute value on K. Right, so that's what I started the lecture with today in the specific case of the p-adic valuation, but it's still true. And it's in fact, it's always going to be actually, it will be an ultrametric or non-Archimedean absolute value always. Okay, so by this I mean that, of course, the absolute value of xy is equal to the absolute value of x times the absolute value of y. That's your usual stuff. The absolute value of x is 0 if and only if x is equal to 0. But the ultrametric part, right, is that the absolute value of x plus y is less than or equal to the max of the absolute value of x, absolute value of y. Right, instead of the usual triangle inequality. And in life, right, there really are only these two kinds of absolute values, like the usual one that satisfies like just the triangle inequality, not like this stronger one. And then all the other absolute values satisfy this stronger inequality, and they all come from evaluation. So that, I mean, that's in a sense what happens the most. Okay. And so now that we have an absolute value, we can complete. I mean, I feel like I'm just repeating what I said yesterday, right? But now it's a field K. It's not like Q and QP, right? Exactly. Yeah. So this is like if I was doing before A is 1 over P, so I don't have to write the negative. Yeah, yeah. Great observation. Yeah. Okay. So we can now complete. Okay, with respect to this valuation. Okay, which is just saying that when you have a series, a sequence that's Cauchy, there's a limit for it, right? You just make up that limit. And what it looked like yesterday was just like declaring certain series that we think don't converge to converge, right? To just be like that's now a number. Like you can now do, the sum of 3 to the n, from n is 0 to infinity, and that's now a legit number, right? I mean, it's kind of weird. Like, what is a completion? It's to just like add symbols that didn't make sense before to your thing now, and now all your limits converge. Okay. And this completed field, Ser, I was gonna say we, I guess we, Ser slash we, denote this field, this completed field, right? That's the important part, by K, and now pointy hat. So that's pretty standard for completion, right? Like the flat hat is pretty standard, I feel, for an algebraic closure, but pointy hat is standard for a completion when you can. Anyway, right? And the valuation V on K extends uniquely to a valuation V hat on K hat, which is also discrete. Okay, why is that? Well, the idea for that is that if there's a little x, right, that's in K hat but not in K, right, so it doesn't have a value yet. So you're like, I have to value this number as well. We value all our numbers, right? Then it means that there's a sequence of elements in K that approaches that. Like, that's what it means to be in a completion, right? The extra stuff comes from there. And this sequence is Cauchy. So at some point, right, so for all epsilon greater than 0, there's n with absolute value of xn minus xm is less than epsilon if nm is greater than n. Okay, the point is that because these are getting closer and you have a discrete valuation, eventually they all have to have the same valuation. And then you just say the valuation of the limit is that valuation, like that they eventually all have. So you can just define it like that. You're like, well, let's see about how big the stuff is that gets to you. That's how big you'll be. That's how much I'll value you. Okay. So the absolute values you know, reach a limit, which is what we call that. Okay. And like, I mean, example, right? If we had, Q with the p-adic valuation for some prime, right? And p is equal to 3, obviously, as usual, right? Then we could take x to be the sum, n is equal to 0 to infinity, 3 to the n, right? 1 plus 3 plus 9 plus 27 plus right? The sequence would be like 1 plus 3, 1 plus 3 plus 9, right? Like they converge to that big infinite sum. And you see, like, I mean, this one has valuation 0. It's not divisible by 3. This one also has valuation 0. It's not divisible by 3. You see that the stuff that I'm adding, like, doesn't change the valuation because I have to add stuff that has small absolute value, right? And the absolute value is, because of the ultrametric, is like governed by the big absolute value stuff. So pretty early on, I mean, this one is like all absolute value 1, right? But I could have like taken a little detour, right? With a convergence sequence, I could have like done something for like 100 terms, and this would be like the 101st term, and then like I get going, right? Okay, so I forget like the other numbers at the beginning, right? Like at some point, you have to start getting serious about converging, and you have to start adding only very small numbers that are not going to change the absolute value, that are unable, because of the ultrametric inequality, to change the absolute value. And so that's why you're just like, at some point, they all have to be the same. Like this, they're always all the same. And you just say, well, that has valuation 0 or absolute value 1, like all the numbers that converge to it. All right. Okay, I'm just going to take 1 more minute to just finish that, and then that's going to be very great. Okay, so then since k hat is a field with a discrete valuation v hat, it has a valuation ring a hat, right, of all the stuff that has positive, non-negative valuation. A is inside of a hat, the valuation ring of the first one, right? And the a hat is the completion of these ones, right? Because of this, the way the valuation extends is like you have to have essentially a sequence of elements of A to get to an element of a hat. Of course, you at the beginning you might have stuff in K because you're being a bad person, but eventually you have to like be in A. Pi is still a uniformizer for a hat. I mean, it's still there and it still has valuation 1. Like nothing has changed on that one, right? And a hat mod pi, right? The ideal pi in a hat is actually equal to a mod pi. So they have the same residue field. Okay, and that's when I'm gonna end today, right? But what I kind of want you to get from these like little lines at the bottom is that passing to the completion changes some stuff. Obviously, now you have hats, right? But also doesn't change too many things. Like it's kind of very mild. You still have the same uniformizer, you still have the same residue field. And so that's something that we do, right? Like the kind of story I want to tell next time when I was talking about the global places is like, you start with Z or Q and like things are hard. So then, you localize and you complete, and all of a sudden you're in ZPQP, and there's more you can say just because things are simpler there when you only have one prime ideal. And the idea is that from localizing to completing, like once you've already kind of gone on that path of having only one prime ideal, there's not that much different, like, you know, you're already in, like you already localized, so you might as well complete and then have a complete DVR and use the theorems for that. So that's where we're going with this. Tomorrow I'm going to talk like a little bit about like local versus global, like just to justify the word local, and then like things that are true, like why are we studying them, right? And then I guess probably last lecture or whatever. Anyway, I'm still hoping to do Newton polygon is what I'm trying to say. All right. Please, no. Now you know what the slide means. I'm a little behind. What time is the talk after? Is it 11:10 or 11:20? 11:10. Okay. So I think that maybe we should take a break and ask questions after. I will be here tonight 7 to 9. So, you know, if you need me, that's a good time to have me. I'll also be outside like during the break, obviously. I mean, not obviously. I could hide under here. You would never find me.
We're gonna take a 10-minute break.
Yeah.
And then we have our guest is here, Anna Mepedowski is here to give a talk. So in 10 minutes, we'll start with her guest lecture. Let's thank Christelle again.
Oh, thank you.